Hey, what's up, Algebra 2? It's Ryan. Today's day 2. We're going over exponential function applications. And these are super important. They come up a lot. So it's really important we understand exponential functions. Okay, so let's get straight into this. Our first problem is y equals 7,500 times 1 plus 0.03 to the x power. So our initial value is always going to be our a value, which is this. It's our number out in front. So in this case, sorry, that's weird. In this case, it's going to be 7,500. And if you're kind of confused on that, just consult the last video. It should be in Google Classroom. And now we're asked for whether this resembles growth or decay. And so what we want to do is we want to look at our b value, which is this, what's inside our parentheses. And so that's going to be, we want to see, is that greater than 1 or less than 1? And so since we're adding 0.03, that's greater than 1. And if we look at our last video, if the b value is greater than 1, that's going to be growth. So that means it's going to look something like this. This is growth. While if it looks maybe something like this, that has a b value of less than 1, and that's decay. So this is b is greater than 1, and then this is b is less than 1. So here, b is greater than 1, so it's going to resemble growth. Now what's our percent change? Well, we want to see how much greater than 1 this is. It's 0.03. 0.03 as a percent is just going to be 3%. So it's 3% change. And, right, we're increasing, so I'm just going to put the positive sign, but it's fine if you just put 3%. Okay, let's move on to 2. Well, what's our b value? What are we multiplying this by? We're actually multiplying this by 1. When we can't see something out in front, when we're multiplying, that's going to be 1. When we're adding, that's going to be 0. But here in this case, our a value is 1. So that's our initial value. We start at 1. And now, is this growth or decay? Well, we see. What's our b value? 0.85. 0.85 is less than 1, so it's going to resemble decay. Now, how much less than 1 is 0.85? Well, let's do 1 minus 0.85. We get 0.15, which is the same thing as 15%. So, 15%. Now, since it is decay, we have to make sure to put that negative sign out front. Okay, this third one, we look at our a value. What's our number out front? 900. Is our b value inside, which is 1.27. Is that greater than or less than 1? It's greater than 1, so it's going to be growth. And then, how much greater than 1 is 1.27? Well, it's 0.27, right? I'm just going to put 0.27, which is the same thing as 25%. Or 27%, sorry. Let's keep on going here. What's our value out front? It's 24,000. Yep. Okay. And our b value inside, well, here we're subtracting 0.08 from 1. So that means it's going to be decay since our b value is less than 1. And how much less than 1 is it? 0.08, which translates to 8%. And by the way, just how we go from decimals to percent is we just multiply by 100. Right? Okay. Here, our initial value is our value up front. In this case, it's 750. Our b value inside, what we're raising to the t power is 1.15, which is greater than 1. So it's growth. So we see a alternating pattern here. And how much greater than 1 is this? 0.15, and that translates to 15%. Now I'm just gonna, up here, sorry. This is negative 8%. Just wanna clear that up, my bad. Okay, let's keep on going. The number out front here is 250,000, which is a lot, right? And just so you know, this initial value is going to indicate what's our y-intercept. So, like, let's just say this is our y-intercept. Here would be our initial point, right? Just wanted to clear that up. Okay, so growth or decay. Well, what's our b value? 0.65, which is less than 1, so it means it's decay. How much less than 1 is it? Well, it's going to be, if we do 1 minus 0.65, we're going to get 0.35, which translates to 35%. And don't forget that negative sign. Okay, from now, this is like muscle memory, right? We look at the number out front, 11,275. We look, is our b value greater than 1? Yes, it is. So it's growth. And then our percent change is going to be 10% because this is 0.1 greater than 1, and 0.1 is 10%. Here, 673 is our a value. That's our number out front. Here, we have 2.2. 2.2 is greater than 1. So this is going to be growth. Now, how much greater is 2.2 than 1? So it's going to be 2.2 is 1 plus 1.2, right? So we're looking at this 1.2, right? And 1.2 as a percent, it's going to be 120%. So this is going to be 120%, right? It's just like all this. Now it's just a big jump. It's a large percent change. Okay, so let's move on to here. So exponential growth / decay, is going to follow this sort of pattern where we have our a value, which we talked about in the last video, which is our initial value, our y-intercept. And then here inside the parentheses is our b value. And so we're assessing our b value by 1 plus or minus r, which is our percent of change. This is this entire column, right? It's sort of what we calculated when we found the difference from 1, right? Then x is, Okay, so here we're given this problem where we're looking at exponential growth, right? So we're doing 1 plus r, right? So here we're saying in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by 92% each year. So we're asked to write a function to represent this data. So we're going to say y equals, and we want to find a. What's our initial value? Well, our initial value is 2,573. Now, this is saying during the next 7 years, the number of incidents increased by 92% each year. So 92% as a decimal, we're sort of going backwards from what we did up here. 92% is just going to be 0.92. So that's equal to r. 1 plus 0.92 is going to equal 1.92. So we're going to say 1.92 to the x power. And that's our equation. Now, how many incidents happened in 2003? So 2003, if we subtract 2003 from 1996, we get 7 years. We're also given 7 years right here. So now 7 years is just going to be our x value. This x is just time, right? So we're going to plug that into our equation. We're going to say y equals 2,573 times 1.92 to the 7th. So if you get out your calculator right now, and we do that, I'm going to first do 1.92 to the 7th power. And then we multiply that. And once I did 1.92 to the 7th power, I got 96.19-ish. And now I'm going to multiply that by 2,573. You should get something, you should get something relatively large. Let's see, I got 247,484, or 400, I'm just going to round to nearest whole number, 485. So it shows there were a lot of computer viruses and other computer security incidences. Okay, let's move on to this example, which is detailing decay. So in this case, now we're doing 1 minus r. Our b value is going to be less than 1 because it's 1 minus r. So it's going to look something like this. Okay, so a new snowmobile costs $12,500. The value of the snowmobile decreases by 15% each year. So let's write an equation for this. Y equals, what's our a value? What's our initial value? It's just going to be 12,500. And then we need to find out our b value. And so we're given our r value, right? It's decreasing by 15% each year. So 15% as a decimal is just 0.15. And since we're decreasing, we're subtracting, right? So we're going to do 1 minus 0.15. That's going to give us 0.85. So we're going to put 0.85 as our b value. Yeah, just a reminder, this is b and this is r. 0.85 to the x power. So let's plug this into our equation. Now we're asked to find what's the value after 7 years. 7 is just going to be equal to x, right? Oops, sorry. Oh, Lord. I'm sorry about that. Oh, God. Okay, wait. Do you guys see that? I have no idea what's happening. Okay. I'm sorry. Okay, x is equal to 7. So let's plug that in. I like to do 0.85 to the 7th power first. I got something like 0.32. Then I just multiply that by 12,500. And when I plug that in, right, this is just going in there into our original equation. Y is going to equal 4,007. I'm just rounding to the nearest whole number because I actually know it here. We'll round to the 100th place just because it's money. Okay, and dollars. Okay, so that's our exponential decay. let's move on to some word problems. So a cup of coffee contains 140 milligrams of caffeine. If caffeine leaves the body at 10% per hour, how long will it take for half of the caffeine to be eliminated from one's body? Will it ever fully leave your body? So let's answer this first question. How long will it take for half of the caffeine to be eliminated from one's body? So what's our initial value? It's going to be 140 milligrams. So that's going to be sort of our A value, right? Our P, our principal amount. So we're going to say 140. Now, we're asked for how long does half of the caffeine, how long does it take for half of the caffeine to leave the body? Well, what's 140? What's half of 140? That's just going to be 70. So we want to see how long does it take to have 70 milligrams in your body once you drink a 140 milligram. Once you drink a cup of coffee that has 140 milligrams of caffeine. So this is going to be our Y value, right? Our Y value would be like amount of caffeine. Amount of caffeine. So we're going to say, oops, my bad. 70 is our Y value. Now, we need to create the equation, right? So our equation, actually I'm going to, I'll do that in a second. Oops, sorry. This is 140. Y equals, well, we already said our starting point was 140. So let's write that out, 140. And then what's our B value? Well, it's leaving, which means it's decreasing at 10% per hour. So 10% as a decimal is 0.1, right? And so since it's leaving, we're going to be doing subtraction. 1 minus 0.1 equals 0.9. So we're going to write 0.9 as our B value. This is our B value. So 0.9 to the x power, where x is each hour, right? Now, remember how I said before, y was the amount of caffeine, and we're trying to find when the amount of caffeine is equal to 70 milligrams? Well, we can just plug that in for y. Sorry, for some reason it's so large. Okay, so we can put 70 in for y here to substitute that in, and now we can just solve for x. So first thing I'm going to do is divide both sides by 140. And you don't even have to find exactly how much half of 140 is. You could really just start, once we do this cancels out, and eventually we get 1/2 equals 0.9 to the x power. Now, what I was saying is you can just start by saying 1/2 equals 0.9 to the x power, because we know it's just, we're asking for half of the caffeine to be eliminated. So we could just jump right there, but for the sake of explanation, I just wrote this all out. So from here, we could use logarithms. We could just say log base 0.9 and then do 1/2. But in this case, what we might want to do is just guess and check, because technically we have not learned logarithms yet. So I'm just going to start plugging in things. I'm going to say 0.9. I know it's probably not going to be, I know it's not going to be 1, because 0.9 to the first power is just 0.9. So let's plug in like 3. 0.9 to the third power. We get 0.729. Let's keep on plugging this in. I'm going to plug in 6. Oops, my bad. To the 6th power. We get 0.53. That seems pretty close. I'm just going to do 0.9 to the 7th power. That gives us 0.78, which is actually closer than 0.478. That's actually closer than 0.53. So I'm just going to say it's somewhere in between 6 and 7. So I'm just going to say 6.5. So if we plug this in, we get x equals 0.65. 6.5. I'm very sorry. Okay. 6.5. And this is hours, right? Now, just for sake of it, I'm going to find the exact number by using logarithms real quick. And the exact number will be something like 0.6579. We're just gonna say this is close enough. You could use guess and check to keep on simplifying it down to find exactly what this x value is going to be. But let's just say 6.5, 6.6, something around there. Just gonna say 6.6 in parentheses. Okay, so the second part of this question is, will it ever fully leave your body? Now the answer is no. Not, at least theoretically it won't. If we're, right, first of all, this is decay. We're leaving. We have a b value of less than 1. So our graph is going to look something like this, right? And this is our axis, something like this, right? And so this is our initial value, which is 140. We calculated maybe what our, where we get 70, so maybe something like there, and then we said this point is like 6.6. Sorry, I don't know what happened. Ooh, gosh, yeah. I'm not super techie, so I don't know what's happening. Okay, 6.6, and then we say like 70, something like that. But if you remember last video, we talk about having a horizontal asymptote. So we have a horizontal asymptote across this x-axis where y equals 1, or y equals 0. So since this is never going to technically reach the x-axis, y is never going to be equal to 0 in this function. So it will never fully leave your body, theoretically. I hope that makes sense. Okay. So the second question asks, a town of 3,200 grows at a rate of 25% each year. Find the size of the city in 10 years and then 15 years. So let's create an equation to model this situation. We have y equals, what's our initial value? 3,200. Now we have to find our b value. So we're seeing growing. So this means when we find our b value, we're going to say 1 plus something. And that something is going to be 25%. 25% is the same thing as 0.25. So r is going to equal 0.25. 1 plus 0.25 equals 1.25. So that's what we're going to put in as our b value. We raise that to the x power, where x is our time in years. And so now we're going to say x equals 10. So we plug that in. I like doing 1.25 to the 10th power first, and I get 9.31-ish, and then I multiply by 3,200, and I get something around 29,802. 802. I'm just going to round to the nearest number in this case. Now let's do 15 years. This is where x equals 15. We just plug it in, right? We plug this 15 in for that x. We do 1.25 to the 15th power. Then we multiply by 3,200. And we get something around 90,949 ish, something around there. Okay, so we see this town is growing very rapidly. Yeah. Okay, let's move on to number 3. This says in 1982, it's kind of hard to see, but in 1982, the number of Starbucks was 5 shops. It has exponentially grown 21% yearly. Let T equal the number of years since 1982. Find an equation for this growth and find the number of Starbucks predicted in 2015. Okay, so let's create an equation. We have y equals, what's our initial value? What's our starting value? 5. So a is going to equal 5. We're going to have 5 out front. That's our y-intercept. And what's our growth or decay rate? Well, here we're talking about growth, right? And so our growth is 21%. And 21% is just the same thing as 0.21. So we're going to say b equal 1 plus 0.21. That gives us as 1.21. 1.21 to the x power. So this is going to be our equation. Or actually not x, I'm sorry. Technically this should be, I'm going to fix this real quick. Yeah, sorry. Technically this should be t based on the variable they gave us. Okay, so this is our equation. Now we're trying to find the number of Starbucks predicted in 2015. That says 2015. Kind of cross that out. Well, if we do 2015 minus 1982, that should be something like, what, 33? I'm not 100% sure. Let me check that real quick. 1982. Yeah, 33. Okay, so this is 33 years later. So this is where t equals 33. So let's plug that into our equation up here. We do 5 times 1.21 to the 33rd power. 1.1 to the 33rd power is like 539.4 multiplied by 5. And we get 2,697 shops, which is good. A lot of Starbucks shops. Okay. Let's do 4 now. Let's just keep on going through this. The depreciation initially, right, when we read this, depreciate means going down. So we're probably going to have decay of some sort. So the depreciation of the value of a car is modeled by the equation y equals 100,000 times 0.85 to the x power, where x is years since 2000. So in what year was the value of the car 61,412.50 cents? So let's create, they already give us the equation. So this is equal to y, right? The value of the car is y. so the value of the car right now is 61,412.5. That's y. So I'm just going to plug that in for this y up here and just say 100,000. We just put commas there. Okay, so now let's do 0.85 to the x power, and we're just trying to solve for x. So let's first divide both sides by 100,000. So once we do this, we get 0.614125 equals point. This happens too often. 0.85 to the x power, and we can. What I'd probably just recommend in this situation, if you don't know logarithms yet, which I think we'll get to later on in this unit, just guess and check, plug in random values for x, and then see where you get really, really close to 0.614125. In this case, I'm just going to use logarithms. And so I do log base 0.85 of 0.614125. We get 3. So actually it works out perfect. And just to check, I'm going to do 0.85 to third power, and we get exactly that. So x is 3, and x is years since 2000. So we just have to remember to say 2000 plus 3. So 2003 was the year. It was about 61,000. And what was the original value of the car? Original value is A, remember? And that's just our number out here. So $100,000. Okay. Now we're going to do compound interest. So Gina deposited $1,500 in it. Or actually, let's analyze this first. So just like before, P is our principal amount. So it's our starting amount, how much money you put into a bank account initially. And then we have R, which is our rate as a decimal. And we sort of talked about that last time, right? Or earlier today. N is going to be the number of times compounded each year. And so we want to notice that it shows up 2 times. Both we divide R by N, and then we also have it in our exponent, multiplying by time. And they'll give us the units for time in each problem. So let's try to apply this new sort of form. It's sort of just a more complex form of the basic y equals a times b to the x power. So let's create an equation for this situation. Gina deposited $1,500 in a bank account that pays 4% interest compounded quarterly. What will the balance be in 2 years? So A equals, well, what's P? What's our starting amount? Principal amount. Well, it's $1,500 because she deposited $1,500 in the bank account. That's our initial value. Now we try to find our B value. So we're doing 1 plus R over N. So first, actually, let's see what R equals. Well, R equals 4%. We get that from this problem. So we say 0.04 because 4% as a decimal is 0.04. And what's N? Well, N we're going to get from here. It's being compounded quarterly. So it's going to be 4. and then t is 2 years. 2. Okay, so here we have 1 plus r over n. 1 plus r is 0.04 over n, sorry, there's that decimal point, over n, which is just 4. So this comes out to be 1.01, right? 0.04 divided by 4 is 0.01. So 1.01, let's plug that in here. And then our n, like we said before, is 4, right? We're compounding this quarterly 4 times each year, times t, which is just 2. So let's do this now. We have 1.01 to the 4 times 2 power, which is just to the 8th power. I got something like 1.083. And now I'm going to multiply that by 1,500. And I get approximately 16,024.29 dollars. So Gina just got like $124 in 2 years, so not bad. Okay, determine the amount of interest earned on a $100,000 investment if it is invested at 5.2% annual interest compounded quarterly for 12 years. Same equation. A equals what's our initial value, what's our starting value? It's going to be 100,000. Now we have to find what's our R value. Well, our R is going to be equal to 5.2%. 5.2% as a decimal is going to be 0.052, right? And by the way, interest is always going to be growth, right? When you have interest, compounded interest over time, you're going to be getting more money for leaving your money in that bank account. Okay, so R equals 0.052. Now we need to talk about N. N is equal to how many times it's compounded each year, quarterly. That's going to be 4. And then time, which is just 12 years, so t equals 12. So 1 plus, remember I'm just using this equation up here, 1 plus r over n, which is 0.052 over 4. We should get 1 plus 0.013, right? That's going to just be 1.013. So let's plug that in here. To the n times t power, so 4 times 12, which is just 48. So let's plug that in. Let's do 1.013 to the 48th power times 100,000. And we get 185,888.87 dollars. Okay. Hopefully you're starting to get a hang of this, or at least sort of understand what we're doing here and how we're using R and N. We're slowly building. We went from this basic form and we're slowly getting more and more complex and applying it to real world scenarios, because this is important when you get a bank account and a Roth IRA and stuff like that. Okay, so Mr. and Mrs. Boyce bought a house for $96,000 in 1995. Real estate values in their area increased approximately 4% each year. What was the value of the house in 2023? So let's create an equation here. A, where A is the value of the house. Our initial value is what? 96,000. Right, that's our starting value. That's how much they bought it for. What's R going to be equal to? Well, R's 4% each year. 4% as a decimal is 0.04. Now we have N, how many times it's compounded. So we're just going to assume N equals 1, right? It's compounded 4% each year. Now, T is going to be equal to, well, we actually have to find out what T is equal to. We're given, we're trying to find how much money it is, or how much it amounts to, what's its value in 2023. And so this equation starts at 1995, so we have to do 2023, our sort of final year, or at least what we're trying to find, minus 1995. So that should come out to be 28, if I'm not mistaken. Yeah, something like that. So T is going to equal 28 years. So let's find our B value by doing 1 plus R over N, which is 0.04 over 1. That's just going to be 1.04. 1.04. Then raise that to the N times T power. 1 times 28 is just 28. So let's do 1.04 to the 28th power. That gives us 3 times 96,000. That's about 875. Yeah, let's just say that. That's good enough. So the value of the house rose from 96,000 to 287,000. That's quite a large increase, so good for them. They made a smart investment. Okay, so you invested $52,400 at 6% for 5 years. What's your total return on investment when you compound quarterly? So all these compound monthly, daily, yearly. This is all referring to N. What does N equal here? So let's create a sort of a base equation here. Let's create, or actually I'm not going to use Y, I'm going to use A. A equals, well, what's our starting value? 52,400. And then we do 1 plus R over N. So I'm just going to write that up here. It's starting to get a little bit messy. Well, R is just going to be 0.06, right? Just from this 6%. So we're going to say 1 plus 0.06 over N, which we're trying to find, actually. I'm just going to write, sorry, I hope it's fine if I just write 1 plus 0.06 over N to the 5, right? T equals 5. They said 5 years. So we're going to say 5N. So now we're just trying to plug in different values for N. Well, compounded quarterly means N equals 4. So we plug this in. In this case, we'll get, I'll write it out. We get 52,400 times, if we do 4, plug 4 in for N, 0.06 divided by 4 is 0.015. So we're going to say 1 plus 0.015 is 1.015 to the 5 times N power, which is just going to be 5 times 4, so it's 20. and we get something like 1.015 to the 20th power. That's going to give us something like 1.35-ish times 52,400. And now we get 70,575. Okay. So that's when we compound quarterly. Oh, and I'm just going to put 0.20 just because it's money. Okay, here it's compounded monthly. There's 12 months in a year, so we're going to say n equals 12. So we plug that in here. We say 52,400 equals 0.06 divided by 12 is going to be 0.005. So we're going to say 1.005. All of this you can do in your calculator if you'd like. You got a lot of decimal places. So here we're going to do to the n times t power. N is equal to 12, t is equal to 5. 12 times 5 is going to be 60. And what are we going to get from this? Well, we do 1.005 to the 60th power. We get 1.35-ish again. Then we do 52,400. So we're going to get something similar but different to compounded quarterly, and we get 70,679.75. Okay, compounded daily. Well, there's 365 days in a year. So we're going to say 5,240 or 52,400. Now we do 1 plus 0.06 divided by n, and n equals 365. I cannot do that, and that's going to be a lot of decimal places. So 0.06 divided by 365 is going to be like 1.6 times 10 to the negative fourth. So if we figure that out, plus 1, that's going to be 1.000 164. Sorry, a lot of decimal places. Maybe we overdid it, but it's alright. Yeah, that should be good. And now we do n times 5, n times t. So 365 times 5 is going to be something around 1,825. So we raise, actually I'm gonna do 1.000164 to the 1825 power is going to be around 1.35 again. Also, just a tip, I've said all these are around 1.35, but they're slightly different, so make sure not to plug in 1.35 into your calculator again and then multiply that by 52,400. Just if you keep on going, if, like, for example, I got my answer 1.34888, I just press the multiplication symbol, then 52,400. That takes my answer from last one. So that's what you want to do, just because these are like so close, so you want to be super precise. And we end up getting 70,681.37. So again, super close to when we compound it monthly, but it's just important to be as precise as possible. That's why I wanted to do a couple of those digits. Okay, so compounded yearly, when we do it yearly, that's just n equals 1. So this is going to be easy. We're going to say 52,400 times 1 plus 0.06 over 1, which is just 0.06. We're going to say 1.06 to the n times t power. So 1 times 5. That's going to be 1.06 to the 5th power times 52,400. 1.06 to the 5th power is just 1.34-ish. And then times 52,400, we end up getting something around 70,123.02. So all of these are super close, but it's slightly different. So we want to be as precise, as precise as possible. Okay, so now we're talking about when we continuously compounded interest. So we're going to use this number called E. E is one of those numbers that just shows up a lot in math. Same, it's sort of like pi. It just shows up. So E is equal to about 2.718. And so this equation, we just say PERT, P-E-R-T. And it's going to be sort of similar to the exponential equations we had before. So P is our principal amount, the amount we start with. That should sound familiar. E is sort of our base. And so E, it looks, since we're using a letter, might look like a variable. It is not. Do not get it mixed up with a variable. It is a number, 2.718. So you don't need to plug anything else into it. It's just 2.718. And then we raise that to R, our rate in decimal, times the time. So let's try to use this PERT equation in number 1, where you deposit $4,000 in an account that pays 6% annual interest compounded continuously. What is your balance after 1 year? So we have A. Well, what's our P? What's our principal amount? I'm going to write this. You know what? I'll write this right here. In this instance, our P is going to be 4,000. It's our starting amount. And then E is just 2.718. So I'm just going to say E. That's really bad. E to the R times T. So R is going to be equal to 0.06. And right, 0.06 is just 6% as the decimal. T is going to be equal to 1 year, right? We're just trying to find our balance after 1 year. So we do E to the RT. R times T is 0.06 times 1, which is going to be the same thing as 0.06. So let's plug this in. We do E. And E is just second, and then the division symbol, at least on my calculator. And so we raise that to the 0.06 power. We get 1.06. And then we multiply that by 4,000. We get something like 4,247.35. Okay. Let's use this again, the same equation. When you deposit $2,000 in an account that pays 4% annual interest compounded continuously, what is the balance after 12.5 years? So A is going to be our balance. What do we start at? What's our initial value? That's just asking how much did we deposit? 2,000. Then we say E to the well, what's our R? What's our rate in decimal? That's 4% as a decimal, which is just 0.04 times, I don't know, that's me getting specific, 0.04 times 12.5 years, which is just our time, right? So let's do E, second division symbol, to the 0.04 times 12.5. We end up getting 1.649, and then we multiply that by 2,000, and we get 3,297.44. Now we're on to the last problem. Scientists use traps to study the Formosan subterranean termite population in New Orleans. The mean number of Y of termites collected annually can be modeled by Y equals 738 times E to the 0.345 times T power, where T is the number of years since 1989. So we're asked to find what is the mean number of termites collected in 1999. So let's actually first analyze this equation they give us, because this is important. Just to understand. Okay, this is our p-value, initial amount. So this is how much we start with in 1989. So that might come up as a question on the test. This is our initial value. This is how much we start with. This is our rate. And you know what, I'm just going to continue this here. 0.345 as a decimal, or as a percent, is just 34. I don't know, maybe that's hard to see. 34.5%, so it's increasing by 34.5%. That's our rate, and T is just our time. And so we're given the time, and we want to find this Y, right? So well, we're not explicitly given the time. We have to find the time. The way we just do that is we have 1999 minus, when do we start? 1989. And so we find out this is 10 years. So I'm just going to plug 10 in up here. T equals 10. So if we plug that into our equation, 738 e to the 0.35 power, times 10, that's going to equal e to the 0.345, sorry, I may have said 35, 0.345 times 10 power, that's going to be 31.5 times 738. We're going to get something like 23,247.29. Actually, I don't know if it would be logical to round to decimals in this case, but that's our answer. That's the population of Formosan subterranean termites in New Orleans. Yeah, probably don't want to go to New Orleans, to be honest. Nah, I'm just kidding. I like New Orleans. Okay, so if you have any questions, go to your teacher. You can come to me, go to the tutoring center, watch YouTube, search up questions on Google, use all of your resources. Just, use all of your resources to make sure you understand, and just ask questions. Okay, thank you. Have a good day.